He did his postdoc at Smithsonian Tropical Research Institute in Panama, and then found his way to University of Guam, where he spent 25 years as a professor, director, and researcher. That's where we first met, those many years ago. After 25 years there, he gave another 10 years at University of Hawaii as the director of the Hawaii Cooperative Fisheries Unit. He was a professor here, University of Hawaii, in the Department of Zoology at the time. And he invented this class. He co-developed it with Dr. John Stimson. So his fingerprints are all over what we do, and we're so glad to have him here today. He's the author of many dozens of published papers and reports. He has worked on Acanthaster planki, which was a major management problem in the 1990s particularly. It's still an issue in some places, the crown of thorns starfish. He's written 2 books, Life and Death of Coral Reefs and Coral Reefs of the Anthropocene, which he, again, has generously donated as our textbook for this course. He has traveled all over the world, spent lots of time on islands. I just love to say their names. Besides Guam, he's worked in Palau and Pohnpei, Kozrai, Chuuk, and a lot in American Samoa. Want to hear about your last trip? And also, if you want to pick up a CD, he's also started up the Coral Reefer Band in Guam. Dr. Birkeland, thank you so much for coming and making the time today.
This is my pleasure because I love to talk about coral reefs. You've seen this slide already, but the main thing I'm going to point out now is this is a very thin film. I think Dr. Hunter said it's about like what covers the bone or the cartilage in your nose. It's in millimeters. It's something between 2 for a branching coral and 4 for a mound coral millimeters. Millimeters is 1,000th of a meter, and then the reef that they accrete goes down like in the Marshall Islands at least 1,300 meters. So you've got thousands of meters, and the tissue is only 1,000th or so of a meter. So that's 1,000,000 times. Then the base of the structure is wider down in the dark, and then there's an awful lot of reef that's no longer covered by living tissue. So it's in at least tens of millions of times more geology than biology in terms of mass. And when I was first starting in coral reefs 42 years ago, the main thing was geology, because the reefs make all this calcium carbonate that's all over the continents and things. A lot of it's secreted by other organisms, but reefs make up a lot of it. Like in the Mid-East, there's a lot of places to find oil because it's very porous. And so the geology of coral reefs is a lot of the geology of oil. Where is it? It's also for aquifers, because on Guam started out as a volcano, but reefs grew out and got thick, 600 feet thick in places, and then the whole reef, the island shifted. And so the north end of Guam is all calcium carbonate or limestone. The south end is all the salt. So the water, the aquifer on Guam, and most of the Marianas is in what used to be coral reefs, because it's porous and it collects the water. So the geology was what coral reef studies were about. It also shapes the face of the world, because places like the Maldives and the Marshalls and the Tuamotu wouldn't be here if it wasn't for corals making above sea level. So back when I was starting, we had the proceedings of the Coral Reef Symposium be one book on geology and one on biology of corals. Now that's really changed. The Coral Reef Journal has 9 editors for biology and 1 for geology, and I'll tell you why. It's a reasonable good thing. It's all we can do. In this class, this is the only one on geology directly, and there's about 30 some on biology. But part of that is because they're always been intertwined, because it's the coral tissue that makes these thousands of meters of reefs, or 1,000 meters plus. And it's also largely animal life that's eroding it away. And so life is everything for geology of reefs. This, don't worry about this, it's just a word that they often use, but we learn about reefs and biology by assuming that what things are happening now was also the way they were happening in the past. And so when they first studied coral reefs, they were up at the top of the Alps in the Switzerland, Italy Alps, and they said that the reefs, the coral told them that these mountains weren't just always sitting there. They were lifted up because corals don't grow on mountains. And Darwin, the same, got all of his ideas about sinking islands and atolls by saying corals that make reefs can't make reefs more than about 60 feet down. They can live a lot deeper, but they don't really deposit so fast they make reefs that far down. And so he's thinking these islands must be sinking, and then the reefs grow up. And he was right. He was a very smart guy because he didn't really see them that well, but he knew from dredging and stuff that the reefs go down. And corals don't grow down there, and so therefore the islands must be sinking. Doesn't know how, and we'll tell you why. Now, Earth is a very special place because most of the universe is hydrogen. The big planets and the stars are mostly hydrogen. But here, we're mostly iron. Oxygen in the upper surfaces is nearly half of everything. And these are the four main elements. But what happened when Earth was forming, it was hot. It's called the Great Iron Catastrophe. Now, catastrophe just means it's not going to go back. It's not going to change. It doesn't mean good or bad. Catastrophe means good in this case because the iron and nickel, the heavy stuff, went down, and then all of the oxygen and carbon and nitrogen, the things that are necessary for life, went up to the surface. But also remember, silica was one of the four main things. Iron went down, and iron and magnesium, the other two main items, a lot to do with the salt or this magma here. But the crust, the silicon and oxygen, well, that makes, instead of basalt, like a volcano makes with lava, the silica and oxygen, which went up, make granite. Now, granite's heavy, but it's only 80% as heavy as the magma. And so once you get up here and it cools, and this is mostly, the crust is mostly granite, that floats on the heavier mantle, which is magma. Now, when you make a volcano, that's heavy, and that's going to sink, but the continents are not going to sink. The continents have basically been here as long as the oldest rocks. And the seafloor has not been here anywhere in the world very long. I mean, in geological time, that's 180 million years is the very oldest, whereas this is 22 times older. The continents are here to stay because they float. And what I always thought was kind of neat is that ice is about 80% the density of water, and so icebergs float. Even though they're solid, they don't sink. Granite is heavy, but it's only 80% by coincidence. I don't think it has anything to do, icebergs and continents don't have anything to do with each other, but I think it kind of blows my mind. They're both about 80%, and so this is basically that the continents are floating around like icebergs. Now, of course, this crust that we have is very good oven. We've lost very little of the heat down here. Of course, heat is continually being generated by radioactive decay, but there's few places where the heat, it does escape. But I think we're going to have these floating continents as long as the Earth because that heat is not going away very fast. And the sun is going to swallow us before any of that changes. Now, as you know, the a ridge down the middle, sort of like a zipper stream down the middle in various places in the oceans is volcanic, and that's where some of the magma comes up and it spreads out. And I got to tell you the story. I was in graduate school, and when I was starting my career, I was worried that science is nothing bad about it, but like religion, where you get fixed on your idea, you're not going to change it. And I thought, am I really that way? Have I really ever changed my mind? Well, a lot of people didn't really think there's lots of evidence, but it's like the shape of things or the distribution. It didn't really have a mechanism, so we didn't really think continents drifted. But when this came out, and he said, this makes new seafloor, and it has to go somewhere, it pushes. So symmetrically, it gets older as it gets close to the continents in both directions. And now we had a mechanism in one paper, I think it was 62, I better check that, but one paper came out, and I saw that and I said, oh, my whole world changed. And the story is that everybody who was at that symposium went back and told their class in the middle of the semester, said, we're changing everything, forget what I told you, you know. And so it's reassuring. I think scientists, if you give them good data and mechanisms, they'll change their mind. Well, it ought to go somewhere, so it goes down and makes volcanoes because you get water down here, and that makes it more explosive. So and here's a picture of the whole thing, and you know this, I guess. Another picture. I'll keep moving. But this really, all of a sudden, in a second or two, it just explained everything. This is why the volcanoes are always around these ridges where things are either coming up and putting out more lava or going under. By the way, there's actually 8 continents. New Zealand and New Caledonia are sitting above, but this is also, I think, mostly granite. And just because the ocean's covering it that's not really ocean, it's a sea, kind of like, you know, the Mediterranean, the Baltic, they're really on the continents. And so this ocean here is really on a continent. That's just not really relevant, I guess. Now, the thing is, there's mostly volcanoes along here, but there are about 40 or so, I think, hot spots where they come up in the middle. And Hawaii is one of those, and I'm sure you know this very well, but the youngest island is here, and it's still growing because it's over a hot spot. But the continental plate's moving northwest, and so these used to be here, and that's when they were made. And once they're made, these are heavy, because unlike continents, these are made of basalt. And so there's a dip. This is actually, the slide is from the late Richard Grigg. And I first heard this in this class. But what I think is really interesting about corals is, you know, the corals are, when the island is sinking, there's a coral reef 4,000 feet down here. We know corals don't live 4,000 feet. So even though, excuse me, even though Hawaii is growing taller, it's doing so as it sinks, and it's making a dip here, and that it's gone down at least 4,000 feet because the coral reef started on the surface. So as it grows, it sinks. And these islands are sinking. And anyway, oceanic islands are heavy because they're made of basalt, and as they cool, they get more dense, and so they sink. Islands on continents may also be made of volcanoes, but they're sitting kind of like, they're heavy, but they're resting on a continent, which is light. So continental islands don't sink, like Guam isn't sinking. It's been there for 40-some million years. Where I don't think there's any island in the Pacific that's over 8 million, although the atolls can be 20 or I think even 80 million years old. Atolls can be very old, but the islands are very young. And this is what happens. You get a volcano like the Big Island, or like, let's say, Hawaii was way back when it was over here, and corals start around the edge. Well, the corals make a reef, but the plate has moved to the northwest, and so this is sunk for a while, making a little dip here, and the corals just keep growing up, and you got a new island being formed. Well, eventually, the island sinks down, and so you got an atoll. There's no more island, but the corals keep growing. And this is what Darwin, the first book that Darwin wrote was about coral reefs, and he was telling all of this. So here you get an atoll. Here there's a lagoon in between because the island's sunk enough and it keeps growing up, but it leaves a lagoon. That's a fringing reef. And then you have a new island, or an island that doesn't sink, and you have I'm sorry, wrong word. This is barrier reef, and this is a fringing reef. And here's a picture. This is a fringing reef, a barrier reef, and an atoll. And to the side, this island is no longer there. You have an atoll. By the way, These are often called islands when you have these things sticking up. And geologically, that's not right. These are just thrown up. This is what used to be an island. It's not an island if it doesn't break the surface. So now we call it seamount or just the base of the atoll. This we call MOTU, M-O-T-U. I like to use that word because it's not an island. It's just a pile of loose rubble. Now this is Guam, and Guam has been here 42 million years. There is no lagoon. Well, I think there might be little ones somewhere, but this is a very old reef, and it's very broad. I think in some places 600 meters. This is Tahiti, which is also the equivalent of the Big Island. It's the youngest one that's broken the surface. This is very close to it. It's only about 6 miles away, and already this island, the Pacific Islands are nice and pointy and jagged and beautiful because they're not very old, and they disappear before they get old, and so they are very not worn down. Guam has been here for 40-some million years, and so much wind and rain that it just now kind of looks like a loaf of bread. It's just not that pretty. I mean, it's a nice place, I know, but it's old. But these islands, they'll be gone, and the reef will stay. That's why islands are all very young if they're oceanic, whereas atolls can be quite old. And so here, this is Motu's. This is the atoll. I guess you call this the base of the atoll or a guyot. It's no longer, it used to be an island. And I just want to show you pictures here because right at the beginning I told you it's only a few millimeters is making thousands of feet of 1,300 meters is 4,000 feet. That's getting close to a mile deep. Look at all this area. And a lot of this is no longer living. It's right out on the edge. It's probably where it's actually accreting. This is a Motu. And this goes for miles. Just how much, that little few millimeters, just how much geology that thing made. And I know I'm showing you too many pictures, but I just can't get over it. Every time I see these, I think, that few millimeters. This is Woolly Eye, I think, and that's miles and miles. I think the whole Pacific Fleet was here once before heading up to. And here, this is not real. I took survey of USGS maps and cut out the pictures. So this is the youngest island in the Carolines. By the way, that's another thing I saw right away soon after they said this is how the continents are moving. And you look at the Pacific plate, you have parallel. The youngest islands are in the southwest and oldest in the northwest, and youngest in the southeast, oldest in the northwest. They're going from southeast to northwest is the Hawaiian Islands, the Carolines, the Samoa Islands. You just look at the Pacific map. They're all going in the same direction, of course. But I don't think anybody really noticed why are they all going in the same direction. But when you see the new idea of continental drift or plate tectonics, well, it pops right out to you. You don't see it until it's there. But anyway, this is Kosrae, Olte, and now look at Chuk. It's a bunch of just little tips. It's not an atoll yet, but this is a big island, and these are gone. And then you go up near Woolly Eye. Now, Hawaiian Islands are different. But this is when the plate was going from south to north, and we go backwards, and then it shifted this way. And what I also think is neat, which you don't see, is right when it made that turn, that's when the Guam and the Southern Marianas formed, and that's probably because they were scraping each other like in California and the Pacific plate are kind of just scraping and making. But once it started moving that way, it started going under and making volcanoes by taking water down and making them explode, and that's when the islands were made from these volcanoes. And so it's wonderful how this all fits together, and you don't see anything until you see one thing. But this is when Guam was formed, and it started going under. But the thing that's different about all of those places I told you, like Samoa and Carolines and the Marshalls, is the atolls keep growing and they don't sink. They're very old, some of them I think are 80 million, but that's not the case with Hawaii. With Hawaii, they start sinking faster than the corals can grow. And that's because you're north of the equator. Most of the atolls are south of the equator, so they're heading into warm water, and so they keep growing. But Hawaiian Islands are north of the equator, so as they go north, it gets colder. As it gets colder, the reefs don't grow as fast, and so eventually the islands are sinking very, very slow. You don't need to worry about buying real estate. I mean, it's real slow. But once the corals get slow enough themselves, reefs aren't made that fast, they start sinking. And this is what Richard Grebe, the guy who told me about the 4,000 feet deep Hawaiian Island reef, he invented the Darwin point. It's where the reefs are growing slower than the islands are sinking. So it's 42 million years ago. I already told you that happens to be the age of Marshall Islands. Now, one thing about geology is it's affected by wave action, and in most, most of the islands, coral reefs do really well when they're in the surge zone. And this is because it brings in oxygen, it takes away sediment, it brings in nutrients, it cleanses it, and so the corals grow out, and they, it's called spur and groove, and they grow out, and the water splits and goes around, and it meets the water coming back, and so it's sort of a very well designed, even though I don't think it was designed, but it's very good for living in surf, because the surf doesn't really hit it hard, it kind of goes around it like a bow of a ship. This side of atolls, it doesn't go that way. It just, at least the ones I've been on here especially, you can walk out, put your fins on, and you're right at the edge, and you can't see the bottom. It's just straight down. And maybe that's special places I've been, but it's the opposite of the windward side, because that's where it grows out. Now, that's the way it usually is. In the south, you have these fingers growing out when you're in the trade wind surf coming in constantly. Hawaii is different, and I think Rooney and Fletcher and others have found that Hawaii used to be like that, but because of oceanography, the waves that are coming in here often are just more than is good. There's a point where wave action is too much. And when you get these things like the jaws of the surfer sea, that's not good for corals. And so Hawaii is very different. Not only are the islands or the reefs sinking as they go far enough north into cold water, the surf here can often be so tough that the best reefs are actually in the protected areas. And so there's good reefs to dive on the Kona coast, but it's protected by these islands. And then on Oahu, there's nice thick reefs of corals, and especially before people there were, but now still in Kaneohe Bay, and also in Hanauma Bay, and on the south side of Molokai and Maui. It's the good reefs are where it's protected, which is sort of a little bit, I mean, you got nice reefs and lagoons too, but it just seems a little backward. Now, wave action, when you have sort of constant surf coming in with the trade winds, like on Guam, I'll show you a picture. It gets a little too much, maybe I'm contradicting myself, because it's not good for corals in real shallow water, and so it's real good for coral and algae. And so the algae are not hurt by wave action, and they actually can grow above sea level because it's always being splashed. Corals need to be in the water, so they can't grow above the sea level, but the coral and algae can. And so in this case, the reef actually goes above sea level because if it's good enough wave action, it's splashed all the time. Now, unlike the northern part of of Hawaii, northern coast, there are corals, but they just start a little deeper, maybe 10 feet down. Then you have areas where corals are they're pretty much most of the time calm, but every now and then they're hit by waves real hard. And this is like American Samoa. The corals get several years where they are growing up because it's beautiful and they want to grow big and tall and branchy, and then every so often they're hit by a hurricane and it really smashes them up. You have areas like Guam, which are constantly hit by typhoons. There's lots of typhoons on Guam, and so the reefs are just like pavements. You've got a lot of corals, but they're all encrusted. It's harder to tell corals apart because you almost have to look at the polyps because they all look like pancakes or fists, like the apostle port grows like a fist rather than branching out. And so the wave action determines here's Guam Marine Lab over here, and you can see this is above sea level, and this is the coral and algal ridge. Coral and algae are also very important for geologically and biologically for cementing the coral skeletons at the base and cementing the reef in general. Because corals, botanists say it's really a botany reef because the coral and algae and the algae are the basis of the food chain, all that. Well, if you're talking about reef, that's the structure. It's the corals that really make the volume. Coral and algae is stronger than coral, but it doesn't add that much volume. The volume is made by corals. And here's a general, this is in the chapter you read, but as you go into high wave energy, as we mentioned, you get a top coral and algal ridge, and then the corals start a little deeper. And as you lose wave energy, they come into shallow water, and if you're in a lagoon, they grow right up to the surface. And the same with turbidity, or not the same, but turbidity is low. The corals have to live more shallow if they're light. This is in a lagoon on Guam again, and you can see corals here grow right up to the surface with no outreach. Now, remember the basaltic islands on the ocean are sinking, and so they're all very young. They don't really record that much history because they're gone. But Guam has been here 42 million years. Now it's staying there. It's on a plate. It's on a floating plate. And so it's not going anywhere. But you have the glacial and interglacial periods. The sea level keeps changing. And so on Guam, it's kind of like you can see where sea level used to be. There is nip in here, and then there's a nip up there. And here, here. And it goes pretty much all around Guam, although it's hard to see from a distance. But you can see there's a groove going around and a groove here. I don't think you see those on Pacific Islands because they're not here long enough. But the continental islands, Guam is a long way from the continent, but it's sitting on a plate. By the way, it's also the closest place to the deepest spot in the ocean, and that's where the Pacific plate's going under and what made the volcanoes originally. Now this, I was just thinking this morning, it was too late to change. This is too complicated, but it's in your book. Let me go through it. This is how corals, geologically structured, react as sea level is changing, like picture on Guam. If the sea level is changing down here, this is sea level, how the speed is sea level. If it's changing slower than the corals can grow, like then what happens you call prograde, I don't think you remember this, but it makes those spur and groove things. The corals grow horizontally, and if there's nothing down there, they just can't grow any further, like on the lee side of the lagoon. But into the waves, they grow. And so this is where you get spur and groove, where the corals are growing faster than the sea level is changing. And then as sea level is about equal or comparable, the reefs grow up. And this is good. And this is pretty much the way it's been. The best time for corals ever had was the late Pliocene, Pleistocene, and now. except for the last 50 years, humans have been making a mess of it. But it was the coral, by the way, I'm jumping around, I'll tell you that tomorrow. But the corals really had it good, and we're making reefs pretty fast up until about 50 years ago. Now, if the sea level is going faster than the corals can grow, and you're on an island, that's not really a problem. You're not have time to make reefs, but the larvae can keep going up into shallow and grow into corals, and it's not changing so fast that you still get your corals. They're backstepping. But if they're retreating, it means the corals are growing this way. Backstepping is they jump from here to here. It's really going fast. Now, if it's really going up fast, then the corals can drown. But this isn't just the sea level going up fast. I think corals can generally keep up with sea level pretty much no matter how fast, even though reefs don't go up. Sea level natural doesn't usually go that fast. But it's a matter of how turbid it is and how much of there is sediment. Like when sea level is coming up now, a person on the backside of Molokai, the lee side, found that just a few centimeters, or just a centimeter or so of increased water height will stir up. It'll go in and start making waves where there wasn't waves and resuspend the sediment. That makes things dirtier. Or when you get a lot of agriculture and construction, so you get a lot of sediment coming off, this makes the water cloudy. And that is also what makes reefs drown. So it's kind of a combination sometimes, is the sea level's going up. The sea level can cause problems that make the water not as good, and also really bad if humans are making the water not as good. So that's when coral reefs drown. And this is, we pretty much covered this. This is backstepping when it goes up very fast. This is very good for coral reefs, and that's an atoll here, as you can see. It's growing in a ring of the islands down here. And when the reefs are growing faster than the sea level, then you start going lateral. And I didn't mention before, if it's coming into an ice age and the sea level is going down because so much of the water is in the ice caps, then they kind of, instead of backstepping like this, they can keep going down because it's still shallow water. Now, the real interesting question is, how old are reefs? Well, they're millions of years old in a sense, like the Great Barrier Reef. But then during the glacial periods, the water was low, so they weren't going up. And so the reefs are millions of years old, and then other times you say the oldest reef is only about 7,000 years old. Now, wait a minute, what are you saying? Well, what they're saying is, you made this reef in the Pleistocene, and when the water comes back, the larvae will preferentially settle on these high spots. They're a good place for corals to grow, is where the corals have made reefs because they're nice structures. They're not in the sediment. And so we're back in business. But when you do sound thing, I forget what you call it, like a sonar thing, and you can see that this is all Holocene reef, and this is Pleistocene reef. So the reef altogether is millions of years old. But the part that we call continuously growing is only about 7,000 years old, but whichever way you're talking about. The same thing with the atolls. The atolls are up to 80 million years old, but probably they stopped growing and only restarted about 7,000 years or so. This is complex geology, is that when a reef starts regrowing on an old reef, it'll make its own reef. But then as it gets older, it'll spread out and fill up with sediment and stuff like this. It'll have its own shape. What this is just saying is you can see the history of reef by taking cores. And if it's always been branching corals, that means it's always been growing very well under good conditions. If it's got mound corals, that means it was living in bad conditions or deep, but then conditions changed where it started getting good again. And of course, if it's bioeroded, that means the reef drowned. With the last 50 years, there's a number of things where reef accretion is slowing down. because it's harder for corals to survive at higher temperatures. They've got to adjust their physiology, and so they have less for growth of tissue and producing eggs and stuff. But also the calcium deposit, the reef accretion, the ability of corals to put on calcium carbonate and make accrete reefs has gone down substantially in the last 50 years. And this is from Bermuda grain coral. Another thing ecologically that's important is reefs. Corals make the reef. They're making three-dimensional structures which are good for fish to hide in, and so they're good for the ecology of reefs. And because there's been a lot of coral mortality because of pollution and sediment and warming, so they bleach, all of this, they're not as healthy, but also, well, I'll get to that. Dead coral is good for bioerosion because the little things that get into the coral and start growing and eroding it from the inside don't go through living tissue. But as you make a dead coral, you get much more bioerosion. And so in the Caribbean, the rugosity, that means the structure, the reefs have become more flat because the branching corals have died of disease and things. And this is from data around the Pacific in the last 45 years. And the rugosity or topographic complexity, structural reefs have gone down. This is a picture saying they didn't do the previous data were not from just one place. They were from both sides of the Caribbean and a good north-south area. So next time I will tell you why I think corals are not going to go extinct. Now maybe some of them will. And remember I said this was the best time, it was recently before humans. Corals that evolved in that time have never faced bad times in the past. They might really have a hard time. But some corals, some genera have been through major extinctions in the past, and I think they're going to still survive. But there's a lot of reasons why the geology is not going to keep up. So you're going to have corals, but they're not going to be making reefs very well. First of all, if there's less living coral, which there is about half in the world is when I started, and there's a lot of data to show that. Even the Great Barrier Reef, which has been very well protected during these times of protection, has gone down 50%. And that was before a major bleaching last year in the northern part, which used to be going okay. So it's less than 50%. I don't know what it is now. But if you have less living coral, then you're going to have less reef accretion. And as you have more barrier coral, and they're going to have more bioerosion, and you have flatter reefs. Now, there's a decrease in pH, which lowers the available carbonate. And so that makes it less accretion. It's less easy to, it's kind of like the corals. It takes more to produce reef than it used to. And also with more stress and repair, that's also less energy the corals have, and again, more bioerosion. Now, while the reef is being made less rapidly, the sea level is probably rising more rapidly. And also there's more resuspension, as I mentioned you, the study on Molokai is the seashore has been that way for thousands of years, and it's just going to make a mess with sediments for a while. With more energy, there not necessarily be more storms, that's weather, but there's more energy to sustain and keep them at high energy. So it's possibly there's stronger storms and less shore protection. Now remember that picture where you could look and see the corals have died. You took a core, several back. This was where I was in a lab in Panama on the Caribbean coast, and Peter Glenn and Ian McIntyre came and did some cores. And this is along the transect. And you can see until about 3,000 years ago, which is something like here, it was acropora, which is the fast-growing coral, but it's the most sensitive to environmental problems. This is just about the time they think that the Indians local Native Americans started agriculture at that time. And they think that may be why it changed to the reef that's there now, which doesn't have any acropora. I was there for 5 years and didn't see any acropora, but it was up the coast. There's a lot of it in the San Blas Islands, which are separated from land. So it looks like 3,000 years ago, humans were having an effect on the near shore reefs. And some other fellows did some other cores and showed the history. And so in this area, they changed very recently, but in other areas there was a change in the past. But acropora used to be much more prevalent in the Caribbean than it is now. And the fact that it's not very prevalent now is partly from disease and partly from bleaching, but partly from the way humans think. Now, remember I said biology affects reefs because biology makes the reefs. The corals and the coral and algae and other things produce the calcium carbonate. At the same time, they take it away. Now, reefs are good places to hide animals from their predators, but they also like to burrow and be safe and not have to defend themselves. And so you have just about every kind of animal group. You have fish, you have chinoderms, you have mollusks, you have crabs, burrowing mollusks, barnacles, sepunculans, polychaetes, and you have all kinds of bacteria, and you have algae that also burrows, and then you have fungus. Just about every kind of living thing wants to make its home in a reef. Well, not every kind of human, but representatives of most groups are microborers, or algae, fungi, bacteria, macroborers. Sponges are major borers. Some of this is good, though. It keeps the reef healthy. Like this is in Hanalma Bay, and you can see all the bite marks are keeping the algae down. It erodes the reef, but it also makes the reef more productive. See, there's not many bite marks on the coral. And one thing I've noticed about parrotfish, at least, is they often avoid, or I should say surgeonfish, is that they don't like to eat the corals. Look at all these bite marks all around, everywhere. This little coral is sign of that. Now they do. There are lots of fish, as you mentioned there, that like puffers, and some species of parrotfish, like the biggest one, the Bulbometapon, really eats coral. So there's a lot of coral-eating fish, and a lot of the Ketodons do, but by and large, they keep the algae down. That's good too. Here's some data from Peter Glenn. The little burrowing bivalves eat 90 metric tons per hectare per year. Sponges are the worst, or almost, they are the worst. And these days, 230 metric tons per hectare per year. You add these up, and you can see that whether reefs are growing or going away is a real balance. Are they secreting the reef fast enough to keep up with all the things that are moving it away? Here's some photographs of a piece of coral burrowing, and then here's, you can see through history, all these little marks are where the parrotfish were eating the algae. These are beautiful pictures from Peter Glenn. I think you'll see that in the book, in the chapter. This is how, as you get more burrowing things in the reef, in the coral skeleton, it makes more holes, or makes it more porous, and this is how the fracture stress goes way down. As you get lots of little holes where the burrows are in the coral skeleton, it makes the skeleton weaker. So if you have a storm, it's more likely to break. Once it breaks, it's going to be like a bowling ball or a stick or something. It knocks against the other corals and hurts their tissue. And if it's a tabletop cropper, it'll be like a bowling ball to knock them off. Then you make more bare space, more bioerosion. So you start a positive feedback. Once you get bioerosion, it weakens the coral becomes a projectile. It makes more broken corals or a lot of scraped tissue. You get more of bioerosion, and so it can keep going like this. I think we're out of time. This is in the book where you read, and this is an important point geologically, is there's a lot of grazing, and it makes silt and sediment. I mean, it makes the sandy beaches are made by parrotfishes and sea urchins. But it not only makes sandy beaches, but it goes into the whole of reefs. And actually, when you look at a fossil reef, it's as much sediment made by the corals as the actual structured coral. Geologists used to think modern reefs are better because you have all this living coral. In the past, they were all mixed with sediment. But now, Hubbard showed, no, that's not true at all. If you're making the reef, it's got a lot of sediment, and the real corals are just a part of it. Too bad that I think I'm out of time, because I got to run.